Now we'll look at section 5.2. I believe that most everything in here is pretty easy to follow. So I guess I could have just said read it and understand it. But I'm going to go through the proofs of these kind of very informally, or I'm not going to, they do some nice two-column proof explanations in here, and I think you can follow them pretty well. So I'll just kind of write some stuff down and kind of explain rather than be real formal. Okay, Theorem 5.9 is something we've been using for a long time, but we really shouldn't have. We have not proven that, we did not prove that the sum of the measures of a triangle is 180. We've been using it a lot, but until now we didn't know it. Until we had parallel lines, we couldn't do this. Okay, so the idea on this is pretty straightforward. Is oh, okay, is let's first draw, and let me make this a different color. We're going to first use that there is a unique line. Whoops, I don't want red. For this, I want blue. Okay. Line through B parallel to AC. Okay, I've drawn it here. Okay, and that forms, well, there's three angles up here at B now. Let's let angle 1 be this angle formed by the line in BA. Let's let angle 2 be angle ABC, what we were calling, you might have called it angle B, but there's several angles up here. And angle 3 be formed by the line and BC. So here's angle 3. Now we know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180 degrees, and that's because they all are three adjacent angles, and the uh, exterior sides form this line. Okay, so those three add up to 180 degrees. Now, we know that angle 1 is congruent to angle A, and angle 3 is congruent to angle C because these are parallel lines. This angle and this angle are alternate interior. This angle and this angle are alternate interior angles. Alternate interior angles from parallel lines. So that means that angle 1 and angle A have the same measure, angle 3 and angle C have the same measure, so the measure of angle A plus the measure of angle, well, this is ABC, plus the measure of angle C is 180 degrees. So we proved that. Okay. Then they do a little more formal, I think, in the book's presentation, but this is the idea, and this is a good way to prove it if you've got some students, is to cut out a triangle with a piece of paper or a piece of cardboard or something, then tear off two corners, okay, like tear off corner A and corner C, then turn them to get so that they fit together here at B, and you'll see that they form that the angle A and angle C form and angle B form a straight line there, and you can convince your students that the three angles add up to 180 degrees. Okay, and here's an exterior angle theorem that's a little stronger than the one we had the other day. Because the one we had the other day said that when you have a triangle here, this exterior angle was greater than either one of those. Okay, we're going to say a little bit more here. An exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. In other words, and again, I'll go through this rather quickly. We know from the previous theorem that the measure of angle A plus the measure of angle B plus a measure of angle, I want this angle, so I'm not going to call it C, I'm going to call it ACB, is 180 degrees. Okay. We also know that the measure of angle ACB plus the measure of angle BCD is 180 degrees. Okay. So you can then substitute some stuff in. So anyway, what do we get then? That the measure of angle okay. So from this one we have measure of angle A plus the measure of angle B is 180 minus the measure of angle ACB. And from this one we have the same thing. We have that 180 minus ACB is a measure of angle BCD. So there's that. If these three add up to 180 and these two add up to 180, then these two are the same as the exterior. Pretty straightforward. Let's do an example. This is number 21 in the text. This is page 255. Okay. We want to find the measure of each numbered angle in this figure. L and M are parallel, and we know that these two segments here are congruent. Okay, so I'm going to put in some extra numbers here that we'll probably need, even though we, well, let's find this one. Let's call this a 5, and let's call this 6. Yeah, I think that's all we need here, if that much. Actually, we don't need 6, do we? Okay, first, let's see. Well, let's just go through here and put some numbers in. What's this angle? Well, this, okay. What is this angle down here? Let me call this 5. Well, I have two parallel lines cut by a transversal, so the measure of angle 5 is 65 degrees because angle 5 and 65 are alternate interior angles. Okay. So we're not really after angle 5 so much as we are angle 3 though, because this little triangle down here is an isosceles triangle. Then the sides, excuse me, the angles that are opposite the congruent sides are congruent, so the measure of angle 3 has to be 65 degrees as well. Okay. Now, angle 1. Angle 1 is exterior to this triangle, so what we just had is the measure of angle 1 is a measure of angle 3 plus a measure of angle 5. So the measure of angle 1 is 130 degrees. Okay, let's see what else we got here. What's a measure of angle 4? Okay. I have two parallel lines cut by a transversal. Okay. Angle 4 and angle, the next 65 degree angle, are interior angles on the same side of the transversal. So the measure of angle 4 plus this 65 degrees have to add up to 180 degrees, right? Okay, they have to be supplementary. So the measure of angle 4 is 180 minus 65, which is 115 degrees. Okay. And finally, we've got a little triangle here, which has angle 4 and angle 2 in it, and 150 degree angle as the exterior. And we know that the 150, based on that 150 degrees is a measure of angle 2 plus a measure of angle 4. So 150 degrees is a measure of angle 2 plus 115 degrees. Subtract 115 from both sides. 35 degrees is the measure of angle 2. And I think we've got everything there. 1, 2, 3, 4. Yep. Okay, pretty straightforward stuff. Okay, let's go back to the book, to the sections here. We're looking at corollaries of 5.9, and those are that the angles add up to 180 degrees. And I'm not going to formally prove these. Let's just point out the important things here. Okay, we didn't have this already. We had side, 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 angle, side, angle, side, angle. What we did not have is angle, angle, side. Okay, and there is no side, side, angle. And there's not angle, angle, angle either. Okay, if two angles in the side of one triangle are congruent respectively to two angles in the side of another, then the triangles are congruent. Okay, so A and D are the same size, B and E are the same size. So the idea here is the measure of angle A plus the measure of angle B plus the measure of angle C has to be 180 degrees. Okay, the same thing for the measure of angle D plus the measure of angle E plus the measure of angle F. 180 degrees. Okay. Since I have some congruences here, these things are congruent. Those things are equal, and from that we get that the measure of angle, oops, okay, the measure of angle C is equal to the measure of angle F. So angle C is congruent to angle F. Okay, and now we have angle, side, angle. So triangles are congruent that way. Okay, I ran through it real quickly, but here's the key point: is you set up one sum equal 180 for one triangle, sum equal 180 for the other. Okay, and then basically you say that the measure of angle C is 180 minus those two, which is the same thing as 180 minus those two, which is the measure of angle F. And then that gives you angle, side, angle. Down here at the bottom, hypotenuse, angle congruence theorem, we have LL and I think hypotenuse L, but we don't have anything involving angles here. On this one, and again, the book is really, they're abusing notation. You shouldn't do this. If I learn of you doing this when you teach geometry, if you're doing this for your students, I'll come back and, I don't know, do something to you. But angles are congruent. When we're talking about numbers, though, we're talking about the measures of angles. Okay, so we have right angles at C and F. We have angle A and angle D are congruent. So the measure of angle A equals a measure of angle D. Okay, And if we take the measure of angle A plus, first off, the measure of angle A plus the measure of angle B is going to equal 90 degrees. Okay, that needs to be stated. That hasn't been said yet. Okay, that the two acute angles in the right triangle have to add up to 90 degrees. Okay. These two are complementary. Okay. Also, the measure of angle D plus the measure of angle E is 90 degrees. A and D are equal, and the measures are equal. So from that, we get that the measure of angle B is congruent to the measure of angle E. I'm leaving some steps out here. It really does take 2 or 3 more steps to do this. Okay. And now we have angle, side, angle. By ASA, the triangles are congruent. Now, as I was looking through things, we've got to do a theorem 5.13, angle bisector theorem. It involves something that I don't think we've ever actually proven here. So we've talked about a little bit about distance, but we've never actually stated or proved that when you're talking about a distance between a point and a line segment, that we're measuring it along a perpendicular. So I made up this little theorem here, which is a quick application of the Pythagorean theorem. It says that the shortest line segment from a point to a line is the perpendicular segment through that point. Okay, so I've got a line L and a point that's not on that line. And again, I'm going to run through this kind of roughly. Okay, let me draw a line here. Oops, try that again, and I want to use a different color here. I don't want to move that point. I want to draw. Can't draw anything on this stupid. Okay, so let's let B be the point on L where PB is perpendicular to L. So B is going to be this point, and this is going to be perpendicular. And let's let A be any other point. On L, so A is going to be here. And we want to show that PA, the distance from P to A, is bigger than the distance from P to B. The shortest distance is going to be measured along a perpendicular. All right. So, because I have a perpendicular here, triangle ABP is a right triangle. Okay. So Pythagorean theorem holds true. PA squared equals AB squared plus BP squared. Okay, or PB squared. Let's call it that. Equals AB squared, this is supposed to be squared, plus PB squared. Now, A is not equal to B, so the distance from A to B is not 0. In particular, then, this number is something plus PB squared, so it's bigger than PB squared. So by the Pythagorean theorem, PA squared is going to be bigger than PB squared. So from that, take the square roots. That's going to be bigger than the square root of PB squared. So we proved it. If you have the distance between a point and a line is measured along a perpendicular there. So the last theorem I want to do is angle bisector theorem, which is actually an if and only if statement. So it's two directions. And I'm going to do both directions, and again I'm going to be a little bit sloppy, or not sloppy, but a little informal, and leave some steps out, and mainly just put down the important things here. So on this slide, I want to look at the forward direction, which basically says if you're on the bisector, then you're equidistant. So I've redrawn the picture here, which is a little bit different than the book. Put some more points and names in here. So the proof for this direction is we suppose P is on the bisector of angle DAE. So, okay. Let's let B be the point on AB, on AD, with PB perpendicular to AB. Okay, so I'm going to let this be a perpendicular. So this distance from B to P, this is the distance from P to this side of the angle. Let's see, be on ray AE. It'll be the point on AE where PC is perpendicular to AC. Okay. What we want to prove is that PB is equal to PC. Okay. So PB is the distance from P to line to this side of the angle, AD. PC is the distance from P to line AE, or ray AE. Okay, so, well, what do we have here? I have then that angle BAP is congruent to angle CAP, and that's because it's a bisector. Okay. I also have that PA is congruent to PA. Okay. And I have right triangles of triangle PBA and triangle PCA. Okay. So, in other words, this is the hypotenuse of one equals the hypotenuse of the other, and one angle is congruent to the other. So by hypotenuse angle, okay, triangle PBA is congruent to triangle PCA, and that means PB is equal to PC, because, well, actually, because they're corresponding parts. And if those two are congruent, They're the same length. Now, the other direction is we're going to be doing, that's only one direction. We got to do the other direction. We have to do this way. Okay. So, in other words, we're going to assume that P is equidistant and have to prove that the angles are, that P is a bisector. Okay. So, in this one, we're going to suppose that PA is perpendicular to, excuse me, not PA, then PB is perpendicular to AB, PC perpendicular to AC, and PB and PC are the same length. We want to prove that angle BAP is congruent to angle CAP. Okay, so what we have is that P is equidistant from the sides. So that's what I'm saying here. The distance, PA is perpendicular, PC is perpendicular, so these two things are distances, and they're the same. They're equal. Okay. And what I want to show is that this angle and this angle are the same. Well, I have note that PA is congruent to PA. That's a rather stupid statement you say, but no, it's part of two different triangles. Okay. So I have two right triangles, and I have hypotenuse leg. So that triangle PBA is congruent to triangle PCA by hypotenuse leg. Okay. And so that means that angle BAP is congruent to angle CAP, which means AP bisects angle BAC. Okay. Angle bisector theorem is really pretty useful in places. Here's one, and this ought to be fun because I'm going to try to use some of the tools on the smart board here to prove this. This is number 31. I've kind of made a simplified version of it here. We have a walking trail or bike path that has a turn this way, so it doesn't have any curves. It has pretty abrupt turns in it. A marker is to be erected somewhere, okay, and X is going to mark the spot. I don't know where. Whoops. Somewhere out here, so that the distance to this and the distance to this and the distance to this are all equal. Okay. How can the position of the marker be determined? What does our angle bisector say? A point is on the bisector if and only if it's equidistant from the sides. In other words, what I did here is if I can find a point on the bisector of this angle, oops, if I can find a point on the bisector of this angle, it'll be equidistant from those two sides. If I can find a point on the bisector of this angle, it'll be equidistant from those two sides. So if I can find a point that's on the bisectors of both angles, we're in business. Okay. So here's where I have fun. Okay. Trying to use the compass tool in the Smartboard program. this is pretty easy to do. Angle bisectors are about the easiest things in the world to do when you're uh, doing some kind of construction, because you don't really even need to you don't need to move. You don't need to change the compass at all. Just pick some sort of distance, put your pointy end down at the vertex, and now, okay, now let's draw of one of these, and I'm going to do the angle bisector where the pointy is. And now let's just draw a circle where it intersects both sides. Now, you don't have to change the angle. You don't have to change the compass any. Put the pointy end down where the curve intersects one of those sides and draw some. Okay. Now take your pointy end and put it down over here. Oops. Just messed up here. I have I can't seem to get this thing, stupid thing. Okay, put your pointy end down over here, and I should be able, there we go, without changing. Now, draw this, and where these two curves intersect, that gives me a point on the bisector. Now, what I'm going to do is I'm going to lighten these guys up a bunch, because otherwise the picture gets kind of hard to see. So the bisector goes through the vertex and that point. Okay. Again, to get the bisector over here, put your pointy end on the vertex and mark a curve which goes from one side of your angle to the other. Okay. And now you don't have to change this. Put the pointy end on one of those spots, mark the curve this way, put the pointy end on the other spot. And mark the curve this way. Okay. And get this rascal out of the way here. And we're looking at the line through this and that intersection point we just found. Okay. So what this means is X marks the spot right there. It's on both angle bisectors. I'm not going to construct the perpendiculars, but if you went from here perpendicular to this guy, it'd be the same as from here perpendicular to this guy, and from here perpendicular to that guy, because of the angle bisector theorem. Okay, well that's section 5 too. Good luck with the problems. I don't think they're particularly hard in this case. I think they're fairly easy. Then we'll get into section 5.3, and that's a little bit different stuff. It's a little bit longer.